All right, so chapter 2, we're talking about one-dimensional motion mostly. And in section 1, we're solving problems in one dimension this time. So the figure here represents the motion of a car along a straight road. So picture that in your mind as you continue to digest the problem. Describe in words the motion of the car. So now we look at the graph. And on the graph, we see a couple of things right off the bat. We see axes, and the labels on the axes show us that on the horizontal axis, we're dealing with t in minutes, so time in minutes. And then we have on the vertical axis, x. So the x here is representing our position in kilometers, okay? So you really need to see those right off the bat, because otherwise, normally, like our x-axis is x, right? But now it's not. The vertical axis is x, position, okay? So the road is being called our position along the x-axis. And the horizontal axis is as time goes on, okay? So you have to adapt your thinking here a little bit. Now, we want to describe in words the motion of the car. So what is the car doing as we travel along time here in our diagram?
Slowing down.
Is it?
No, it's going like backwards.
I think slowing down because it says it's kilometers 10
It
kilometers
it
down
backs up.
negative 20.
Because, let's say,
Is it backing up?
I say slow.
no, well, okay.
You wouldn't back up
Well,
for
that's what I'm trying to say. So, because it starts, let's say, this is the car,
Uh-huh.
this is your origin.
Uh-huh.
You're starting at 10 though, well, now you go reverse. So they back
Okay,
up
so
past
what
the-
you're doing
past
is
the-
you're making a
past the
visual approach to this, which is great. That's a good idea.
They back up past the origin.
Mhm.
They turn, and then they very slowly start to go. There's
Okay.
a small period of time where they stay in that same spot. Then they slowly start moving again,
Move forward,
back
though.
towards where the origin
All right.
is.
So there's a few things that you said there that we need to talk about, but the first idea for sure was great. You made a visual approach and you said, okay, here is the origin. Their position is 0 right there. All right? So now, where are they to start? When time is 0, where are they?
10 kilometers in front of
Time
the
0 to
origin.
0.
10 kilometers in front, right? So over here, 10 kilometers. And we should put some sort of reference on here. So positive x is to the right, right? Like we can put a positive y on here also. Even though it's not going up, it's just going to the left and to the right. So now we know which way is positive direction. So 10 kilometers to the right, its position is 10 kilometers to the right. Now what's happening?
Now they go.
According to the diagram, it's as time goes on, it's getting closer and closer and closer to a position of 0 from the origin, right? So it's moving that way in the beginning. Eventually, does it get to 0?
Yes.
Yeah, what time?
10 minutes.
So this is t equals 0 minutes. And then at 10 minutes in, right there, its position is 0 kilometers at t equals 10 minutes. Which way is it moving at that point? How do you know it's still moving to the left?
Because it keeps on going down. So
Because what keeps going down?
The kilometers.
Position.
The position.
Yeah.
Okay, yeah. So the position keeps moving in this direction here. Okay, so you guys are still talking about position, which is fine. So where do we end up then?
Negative 20.
Negative 20 kilometers. So that means where?
After 30 minutes.
But where are we? What's negative 20 kilometers mean?
Backward. We're just behind the origin.
Where?
To the left.
Left of the origin, 20 kilometers. So we're over here now, 20 kilometers. So remember, distance is not negative. To say negative 20 kilometers, you need a position and a direction. Okay, it's almost a vector, right?
That's it.
And that's at 30 minutes, that's right. So we're gonna say t equals 30 minutes. But there's more. Now what?
There's one.
Now, when does it reach 80 back at 0?
Well, what happens right here?
Stop.
It stops moving for 10
10 minutes.
Our position stays there
For 10 minutes.
for 10 minutes. So t equals 30 minutes to 40 minutes, right? Okay, now what?
Goes to the right. Goes
Yep.
positive.
We go 20 kilometers to the right.
So now we're moving this way. I'm gonna change colors just so that we're seeing that we're, okay, doing that. So now we're moving to the right. How do you know we're moving to the right?
Because our position starts getting more positive.
The position is starting to go positive. It's good, it's getting closer to the origin now from where we are. Okay, so give me something.
We then put under the 0 kilometers and the t 10 minutes, and we put
T
t
40.
equals 80 minutes.
40.
It'd be 80.
So we would have,
Because when it reaches 0 at the origin again, it's 80 minutes.
okay, so t equals 80 minutes also?
Yeah.
And we have another easy point right here too, right?
Yep.
Negative
Negative
10,
10 kilometers.
60.
Okay,
Negative
so
10,
that would
10
be
kilometers.
10 kilometers. And that's at t equals 60 minutes?
Yeah.
Okay, all the while we're moving to the right. Okay, so right here, we're at the origin. Now, the whole time you guys were talking about position. But how fast were we going?
We don't know.
Well, you could
Yeah.
almost, well, there's two different speeds.
It went,
Because
kilometers
when they're decreasing from 10, and then they pass through the origin and go to the left of the origin, they're going one speed.
Mhm.
But then when they stop the 10 minutes and then start going again, that's a different speed.
Right,
And so it's, well, if they're moving 10 kilometers for every 10 minutes.
okay.
What?
Yeah, because he times it by 6 to match up
Yeah,
minutes into hours.
So we have
Okay.
a position here, right? And a position here. Can we calculate the slope of that line? We've talked about this before, right?
Yeah.
The slope of that line would tell us the speed, the average speed, not the instantaneous speed, just the average. So we could say the speed, which we use v for velocity, equals, we would need a y2 minus a y1 over an x2 minus an x1, just like algebra 1, right? Okay, so give me a final speed, or a final position minus an initial position.
Negative 20.
Negative 20 minus the initial position, which was positive 10. So negative 20 minus 10,
negative
Over
10.
30 minus 10, minus 0.
30 minus 0. Okay, now the only problem with what you guys told me here is we're missing the units. Okay? What are the units on the top?
Kilometers.
Kilometers.
No.
Oh, minutes.
Actually, yes. Sorry. KM. Sorry, that was my bad. KM, and then this is minutes.
Yeah.
Okay. So we have negative 20 minus 10, negative 30. Divide by
30.
30.
30, so negative 30 kilometers, and we have 30 minutes. 30 divided by 30 is 1, so we get negative 1 kilometer per minute. So when we're moving to the left, we have negative 1 kilometer per minute as our speed, our average speed. What is our speed, our average speed to the right? Tell me what to do. V equals what?
For the one going from negative 20 to 0.
So 0 minus 0 plus 20?
Okay, for the y coordinate,
Yeah, for the y.
0,
Minus 20.
0,
So plus 20.
0, kilometers minus
30 kilometers.
negative 20, so plus 20 kilometers over,
over 80 minutes. minus
Okay.
40.
minus, it was 40 minutes.
Yeah,
All right, what do we get?
20 kilometers,
over 40 minutes.
40 minutes, which is 2 kilometers,
It's not 2.
or sorry,
25.
Yeah, 1 kilometer every 2 minutes.
1 kilometer every 2 minutes, or 1/2 a kilometer per
a
minute,
kilometer,
yeah.
or 0.5 kilometer per minute. Okay, so we have our speeds now. What about the one that I circled in green there?
The stop.
0 kilometers for 10 minutes.
0 kilometers per minute. We're not moving.
You know what this reminds me of for this model?
Okay, so now in words, what is going on here?
like I said, they,
Moving to the left, or if we knew east-west, we could say like to the west maybe, right? Moving to the left at what?
at 0.5 kilometers.
To the left, we're going
One
negative
kilometer
1
per second.
kilometer per minute.
Oh, per minute, yeah.
Okay. For how long? Or for how far?
For 30 minutes.
Okay, you could say 30 minutes. Then what happened?
And we stop for 10.
Stop for 10 minutes. Then what?
Then go left for,
Then move to the right.
move to the right. Oh,
At what?
0.5 kilometers.
For
Or 40 minutes.
was 40 minutes? Okay. So we had to do some math there to figure all that out, but then we could write the words, okay? We had the concept of what was going on, but not the specifics of the numbers that needed to be in there to be able to completely write the words. Okay, make sense? Okay. All right, so now relating the position to velocity is kind of what we just did, right? The slope of the graph is the rise over the run, which is the delta x over the delta t. So the change in position over change in time. So that's a big deal for us. We're going to be using that constantly. For velocity, change in position over change in time is what we're calculating. So delta x over delta t. We will use change in position over change in time in the x direction. So that would be finding the velocity in the x direction. V sub x equals delta x over delta t. We might be working in the y direction. V sub y, the velocity in the y direction, equals the change in position in the y direction over delta t. This notation with the subscript is very important because when we start putting the two directions together, the motion in 2 dimensions, so we're moving in both the x direction and the y direction at the same time, like a projectile does, throw a ball, goes up and down and left and right, right? Then we'll need v sub x and v sub y in the same problem, okay? So we want to start getting used to this notation where we have the subscript going on here and the subscript here, okay? So a faster speed means a steeper slope. We saw that with the position versus time graphs already. The slope of an object's position versus time graph is the object's velocity at that point in the motion. So the object's velocity and the slope on the position versus time graph are the same. This also corresponds to a negative slope and a negative velocity. Negative velocity okay? Not negative speed. Speed is not negative. Velocity can be negative because it describes a direction of travel as well. The direction of motion on a position versus time graph is determined by the sign of the slope. That's why it's velocity here, not speed. Okay? If I have a negative slope, it's telling me that I'm going against the direction of positive. So if this is my standard coordinate system with positive x and positive y, and I have a negative slope, it's telling me that I'm either going against the positive x direction, which would mean I'm going that way, or I'm going against the positive y direction, which would mean I'm going that way. Okay? Make sense?
Yeah.
Okay. All right. So now, given the car's position versus time graph, draw its velocity versus time graph, and then describe the motion. So these are kind of tricky when you're first starting out. What you have to do is think about what the velocity is. So you kind of have to do a calculation. You don't necessarily have to do like the physical, like write down m equals y2 minus 1, like you do in Algebra 1, but you do have to at least think about it, okay? So what I like to do is, if I'm given the graph, like I have it on a piece of paper, what I'll do is I'll just extend the graph down like this. So I just drop the axis down, and then I'll extend a new axis out so that my scales are going to line up. And what I want to do is kind of correspond the key points, the key moments in time. So like this 2 seconds right here is going to be an important moment in time. The 4 seconds right here is going to be an important moment in time, right? So this is going to be time in seconds again. And then this is going to be not position x, but velocity, so v. And then it's not meters, but it's going to be, we had meters here and seconds here, and we know that when we calculate slope, it's going to be meters divided by seconds, so it's going to be meters per second. So we're going to write meters per second here. So that's how you set that up. Now the next thing we're going to do is figure out what was the slope of the original graph during those segments of time, okay? Because that's going to be the velocity during that time. So for the first segment, what was the slope?
-2.
So yeah, you have a change in y of -2 and a change in x of -4 and a change in x of 2. So you divide and you get -2, right? Okay, so then that means we're going to need -2, and that's going to go on for 2 units of time. Okay, so notice how this is going to line up now for us. Okay, so then what we're going to do is we're going to draw a segment from 0 over to 2 because that's a constant slope there. For that line segment, it was a slope of 2 the entire time. So we draw a horizontal segment that's supposed to be horizontal. We draw a horizontal segment over at -2, okay? And I want to label that -2 there so that I know what it is. Okay, now what happened on my next segment of the original graph?
-2.
Yeah, that's the slope of -2, right?
Oh yeah.
Okay, so I'm at -2, horizontal segment. Okay, what happened on the next segment of time?
They stop for 2 seconds.
They stopped, so what's their velocity going to be?
0.
Right. So notice how I'm going to line this up, okay? And you don't have to draw those dotted lines. I'm just doing that for demonstration. You can. There's nothing wrong with it. In fact, I like it if you do, but you don't have to, all right? So for right now, we have a slope of 0. We're not moving. So our velocity graph is going to show what? At 0, a horizontal segment. That's right. So right here, we just got to make sure that we can see it, okay? So there we are. Wow, a slope of 0. I don't know why it's not drawing. Okay, there we go. That's pretty good. Okay. Now what happened on the next segment?
It went up 10. in 2
From
seconds.
-4 to +6, that's a change of 10
In 2 seconds.
in 2 seconds.
So 5.
So that's a slope of 5, that's right. So now in this segment of time, right? So from out to positive 6. So here's 6 out here. This is 2. This is 4. So we need to be all the way up to 5. So 1, 2, 3, 4, 5. This is just a sketch. It doesn't have to be 100% beautiful. Where are we going to be?
A line up from 4 to 6 at 5.
Yes, we go up to 5, and it's going to be a horizontal segment right there, and that's it. Okay? So, given the car's position versus time graph, draw its velocity versus time graph. We have velocity labeled, we have time labeled, so that's a velocity versus time graph. Describe the motion. What is the car doing?
Going backwards, stopping a bit.
Is it going backwards? We don't know
Yeah.
what direction it's facing, right?
be pulling
All we can do is we can say in a standard coordinate system that looks like that, right? What direction is it going?
Down.
Down?
Yeah.
The car is going down.
It's going left.
It's moving left.
Oh, yeah. Oh, okay. Left, yeah.
From the origin, it's moving to the left because it's getting farther away to the left of the origin, right? Or you can say, well, look at the velocity here, right? It has a negative velocity, which means it's moving in the direction opposite the positive, which means it has to be moving to the left. So it's moving to the left at what?
2 seconds.
At 2 meters per second for how long?
2 seconds.
2 seconds. Then what?
Then we stop for 2 seconds.
Stop for 2 seconds. Then what?
Then we go right at 5 meters per second for 2 seconds.
At 5 meters per second for 2 seconds. You got it. Okay? So being able to draw the velocity versus time graph from the position versus time graph is really important. And then being able to describe the motion from the position versus time graph, which we just did before, but now being able to describe the motion from the velocity versus time graph is also important. And that's kind of what we just did now. All right, so imagine you leave this room and begin walking at a constant rate of 1 meter per second to your next class, which is down at the end of the hall. At 15 meters along the way, you realize you left your phone in here, but the bell's about to ring, so you turn around and run back at 3 meters per second to retrieve your phone. Draw a velocity versus time graph to model the situation, then draw a position versus time graph. So we want the velocity versus time graph first. All right?
Yeah.
So, what do we do?
The T, the sideways T.
Okay, good. So we're going to do this, like so. Now what?
Label the ends. So the top is going to be V and meters per second.
Good.
And then the other one's going to be T in seconds.
Time in seconds. All right, now what?
Our slope is 1 meter per second.
So this is the velocity versus time. What is our velocity at first?
1 meter per second.
Constant?
Constant rate.
Constant velocity. So we have 1 meter per second. So this would be -1, this would be +1. Now, which way is positive? We have to think about that for a second. Let me find a little space here. Normally, we have our standard coordinate system, +x, +y. Which way do you want to say is the positive direction? Like visualize walk out of the room, you're going to walk down the hall. Is walking down the hall positive direction or negative direction? Negative direction? Okay, fine.
Yeah.
So what is our velocity when we walk down the hall?
-1.
-1, fine. Okay, so how long do we walk down the hall?
For 15 meters.
For 15 meters.
So 15 seconds.
So that means it took us 15 seconds to do that. So that means we need to mark 15 seconds on our little sketch, right? It's just a sketch, so that's the beauty of it. You can just make 15 seconds somewhere. So 15 goes there. Now, how does this look? What do we do? Is this some kind of line that
We
goes
make
up?
the line to 15 seconds at -1.
So to the origin, or what does it do?
From the origin at -1 to 15 seconds
On the origin, so right on the axis,
at -1.
and then up to 15, so
Uh,
diagonal line?
Straight line.
All
Make a
lines
dotted
are
line.
straight.
Make a dotted line from 15.
A dotted line?
Yeah.
I'm drawing a
So
dotted
it's
line
like a
right now?
segment. From 15.
You're missing a word. What kind of line am I drawing?
Linear.
Straight.
All lines are linear and straight. That's like the
Horizontal,
definition.
horizontal.
A horizontal line, good. So we're drawing a horizontal segment over to 15. That's supposed to be horizontal, it's supposed to stop at 15. I'm gonna try again.
Can we still make those dotted lines?
Absolutely, if you like those dotted lines, draw them in there. So here we are, I put some dots in there so that you know, look at that, straight dots all the way down, perfect. Okay, now what? Okay, 15 seconds in, 15 meters in, we stopped, we realized we don't have our phone.
Turn around.
Okay, we turn around instantly, and what happens?
We run back at 3 meters per second.
Okay, so 3 meters per second, so what do I gotta do?
Go up 3, or go up 4.
Go up to 3, positive 3.
Positive 3 on my velocity axis. Here's 3. And then what?
Draw a
Go
straight
back from 15 to 0. No, that's seconds. Go 15 to 30.
30?
Yeah, because it's the same.
No, so it's.
Oh, no.
So it's 5 seconds.
Okay, what'd you say?
Since it's 15 meters,
It's
you're only
5
seconds
meters.
away if you do that.
So,
5 seconds.
that's right, we're going 3 meters per second now, we only gotta go 5 meters, so or 15 meters, so it's only gonna take us 5 seconds to get there.
So the next one would
20?
be 20.
So 20. Okay, and how am I gonna draw this one? Try to do a little bit better this time?
Horizontal line.
Horizontal segment from
Dotted.
15 to 20, and that's it.
No, we describe. Oh, position time.
Position versus time, okay. So I don't have room to do it underneath. It's better to do it underneath if you can, but I don't have the room to do that, so I'm gonna go here. Okay, how do I label this one?
Time in seconds and position in meters.
How do I say position?
X.
Okay, yep. X in meters. Okay, now what? What should definitely be on my horizontal axis for labels?
1. Wait. 1 second. 15 meters?
15 seconds.
15 seconds
Oh, yeah, and 20.
and 20 seconds. Those are the key moments in time that happened, right?
Because you undid the dog one in the other one.
Uh-huh. Okay, now what about the position?
Position 3, 1, and -1.
No.
15.
Where were we at the start of time?
Oh, origin.
0.
We were in the class, which was the origin, right? So we're right here to start. Oops, let me change color. Right here to start. Okay, now where did we go?
15 meters down.
Why down?
Because it's negative.
Because we went in the negative direction.
So negative.
So we're gonna mark 15 meters, so -5, -10, -15 maybe, like that. Okay, and where do we hit -15 meters?
At 15 seconds.
At 15 seconds. So that's right there. Well, how's it gonna look from 0 time to 15 seconds time?
Straight line.
Okay, good. Like that. Okay, now what happens?
And then we draw a line from that dot that we just made to 20.
Yes. Now we turn around and go back to the classroom, which is on the axis. That's it. Good. Now, how does this look physically? Like if we were to sketch this out, we would draw the hallway, right? Representing the hallway. And the door to the classroom would be like right here.
That's 0.
And this is the origin, okay? So the hallway is longer to the left than it is to the right. To the left is negative, to the right is positive. We already have that up here.
So left 15.
So we would go
0.
15 over here. And what did we do? We went this way, and then we turned around and came back this way. Okay? And that's kind of not what we had to do on this problem, but that's the idea of the concept of what we did to be able to sketch out the velocity versus time graph and the position versus time graph. Okay? All right, so that's the idea. That's pretty much what you're doing on the homework for this section. So there you go.